this set of notes, we're going to look at some continuous distributions. The first one we're going to look at is what is called the uniform probability distribution. And we're going to start out with an example. Suppose a student will need between 15 and 30 minutes to take a quiz. Assume that the probability the student needs between 15 and 20 minutes is the same as the probability she needs between 25 and 30 minutes. In fact, if two subintervals are of the same length, they have the same probability. Let y be the length of time the student takes. Find the probability the student takes at least 25 minutes. So let's start out by drawing the graph of what this distribution looks like. So if we have here on our axes, and let me make my pen size just a little bit smaller here. So here we've got f of y, and here we're going to have y. So what we're saying is we know the student needs anywhere between 15 and 30 minutes to take the quiz. And we know that the probability for any subinterval in between there is the same. So in other words, from 15 to 30, we have the same value for f of y. Now, this is a continuous distribution, so we're going to talk about area underneath of this curve. So typically how we'll draw these is we're actually going to draw a rectangle, and I'm going to have dotted vertical lines. And the reason for this is since we're working with a continuous distribution, we know that the probability that y is equal to 15 exactly is 0. So we don't want to give the false impression that we have area above the 15 and the 30, so that's why we use dotted lines. Now, the next thing that we know is since this is a distribution, we know that the total area has to be equal to 1. So looking here, we can see that the length that this rectangle creates is 15. And if we need the total area to be equal to 1, if we consider the length times the width, we know that it has to be equal to 1, and that we know our length is equal to 30 minus 15. So what this tells us is the width has to be equal to 1 over 15. In other words, over here on the y-axis, we have 1 over 15. Now, the probability that we're interested in is that the student takes at least 25 minutes. So if 25 were here, what we're really interested in is this area under this curve. So in other words, what we want to know is the probability that y is greater than or equal to 25. And we can see, since this curve is actually a rectangle, that's going to be equal to the length of the green portion, which is equal to 5, times the width, which is 1 over 15. Now, alternatively, since this is a continuous distribution, we could use calculus like we've seen before, and what we could do is we could integrate from 25 to 30 our PDF, which notice in this case is just 1 over 15 dy. And if you go through and do this integration, you'll find out that this is equal to 1/3. So notice if we wanted to write out what f of y was for that example, we could say that f of y is equal to 1 over 15 when y is between 15 and 30 and 0 otherwise. More generally, we could write the uniform probability distribution as follows. If theta 1 is less than theta 2, and these are going to be two different parameters, and just for example, in our previous example, we had that theta 1 was equal to 15 and theta 2 was equal to 30, a random variable y is said to have a continuous uniform probability distribution on that interval if and only if we have this density. And so notice this density right here is exactly what we found for our example. Because in the denominator, that theta 2 minus theta 1 for our example was equal to 30 minus 15. And generally what we'll say is we'll say that y is distributed uniform, theta 1, theta 2. So again, note that theta 1 and theta 2, those are parameters. And the constants that determine the specific form of the density function, we call those parameters of the density function. So we saw this when we worked with the discrete distributions as well. And it ends up there's a relationship between the uniform probability distribution and the Poisson. If we have a Poisson distribution and it's known that exactly one occurrence happened in the interval from 0 to t, then the actual time of occurrence is uniformly distributed over 0 to t. And so let's look at an example of that. The number of drivers passing through a tunnel has a Poisson distribution. Suppose it is known that during a 5-minute period, one car passes through the tunnel. Find the probability that the car entered during the middle 3 minutes of that time period. So notice here, we know that y is distributed uniform 0 to 5. And our f of y in this case is going to be equal to 1/5 if y is between 0 and 5 and 0 otherwise. And so let's look at our plot. And if we're interested in the middle 3 minutes, that means we're interested in the probability that y is between 1 and 4. So looking at our plot, what we're interested in is this area under the curve. And notice that that is going to be equal to 4 minus 1 times 1/5. Which is equal to 3/5. And similar to before, we could have also used integration. And then here we have the R code to find those as well. Just like with any distribution, we can talk about the mean, the variance, and the standard deviation. And for the uniform distribution, we have the formula for the mean and the formula for the variance. So if we go back to that original quiz example that we had earlier, let's find the mean and the variance. Recall for that example, theta 1 was equal to 15 and theta 2 was equal to 30. So if we want to find the mean, we know that the mean is equal to theta 1 plus theta 2 divided by 2, which in this case is 15 plus 30 divided by 2, which is equal to 22.5. And let's go back up to our quiz example. Notice that 22.5 falls right in the middle of our rectangle. In addition to the mean, we can also find the variance. So our variance is going to be equal to theta 2 minus theta 1 squared divided by 12, which is equal to 30 minus 15 squared divided by 12, which is equal to 18.75. Now, arguably the most important continuous distribution when it comes to statistics is the normal probability distribution. It is used quite often. The reason for this is, and we'll talk about this as we move forward in the course, is it ends up that many common statistics that we work with, those statistics follow a normal distribution. There are other distributions that statistics follow as well that we're going to look at in this module. So again, the normal distribution is a very important distribution. We can see here is its probability distribution, and you'll notice that its probability distribution is controlled by two parameters. They are mu and they are sigma. So over here, looking at this plot, we can see what mu and sigma do respectively for the normal distribution. Mu controls where the center of the distribution is. So if we look at the yellow, the red, and the blue curve, notice that all three of those have mu equal to 0, and all three of those distributions are centered at 0. Whereas the green curve has mu equal to -2, and it is centered at -2. We could also look at the spread. Sigma controls the spread. So notice that the yellow, the red, and the blue curve all have the same center, but if we look at the spread, we'll notice that the red has a larger variance than the blue, and the yellow has a larger variance than both the red and the blue. So notice that as the variance increases, the curve starts to spread out. And so one reason that it flattens as it spreads out is, remember that all of these curves have to have a total area of 1 underneath of them. Looking at the mean and the variance of the normal distribution, you'll notice that the mean does occur at mu and the variance is sigma squared. So in order to find the area under a normal curve, we could use integration, but unfortunately a closed form expression of the integral does not exist. So generally what we will do is we will either work with tables or software to help us out. Probably in your intro stats course, you probably used what's called a standard normal table. And so the idea is that any distribution, or probably any normal distribution, can be converted to a standard normal distribution, and then we can use standard normal tables to help us find the areas under the curve. Well, now with access to computers and software, we don't actually have to do that transformation anymore. We can easily work with whatever normal we want to. So for this particular course, since most people have seen the standard normal and worked with standard normal tables, instead we're going to work directly with the normal distribution that we're interested in. And we can do that using R, and here is the R code. Alright, so let's look at a couple examples and how we would go about solving these. Suppose that any given day's gross receipts in thousands of dollars from a large store are normally distributed with mean 20 and standard deviation equal to 2. Find the probability that on a certain day those gross receipts are between 15,000 and 18,000. So whenever I work with a normal distribution, I think it's always a good idea to start by drawing what that curve looks like. So here's my normal curve. And I notice, or I know rather, that the mean is at 20,000. And the probability that I'm interested in here is I'm interested in the probability, well, if my random variable is y, of y being between 15,000 and 18,000. So coming down here, I'm interested in between 15 and 18, and again, assuming these are in thousands. And if I draw the area, this is the area that I'm interested in. So in order to find this area, I can use R to help me out, and I'm actually going to use two pieces of code. Notice that if I look at the area to the left of 20, and I subtract off the area to the left of 15, I will be left with the green area, which is what I am interested in. So looking up here at the top at our R code, notice that the p-norm function can help me out. So in R, if I use p-norm, oh, and sorry, I just realized in my picture I extended that over too far. Let me erase that and fix that picture really quick. The area we're interested in is at 18, not at 20. There we go. That's correct now. So p-norm will help me find the area to the left of 18. And I need to give it both the mean for this distribution, which is 20, and a standard deviation of 2. Now, alternatively, since these values are in thousands, I could have wrote this as 18,000, 20,000, and 2,000. Either way will give you the same answer. So that's going to give me the area to the left of 18, and then I need to subtract off the area to the left of 15. This is still falling under the same normal. And if you put that in R, you should find the following value. Let's look at another example. Intelligence tests assess a person's mental abilities and compare them with the abilities of other people through the use of numeric scores. Although the term intelligence is used as if there is an agreement on what that means, in reality there is so much debate as to how this term should be and has been defined. So typically IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. So we could ask, what is the probability that a randomly selected patient scores below a 95? So again, thinking about what my normal distribution looks like, we know it has a mean of 100. And if I'm interested in the value 95, and I want to know the probability that we score less than 95, that's the same as finding the area under this normal curve. Notice this is a cumulative probability because I'm saying I'm interested in the probability that y is less than or equal to 95. So we can use r again, and again we'll use that p-norm function. So the value that I want the area to the left of is 95 for a normal distribution which has mean 100 and a standard deviation equal to 15. And if you put that in r, the value we will find is equal to 0.3694. Now we may also be interested in percentiles. So if I want to find the percentile here, what I'm saying is the opposite of what we had before. Instead of giving the endpoint that I'm interested in, what I'm saying is here the area under the curve is equal to 0.85, and I want to find this value right here. Well, if we go back up to our R code, notice the pth quantile function can help us out here. So here I want to use Q norm, and I want to find the endpoint that has area 0.85 to the left of it when that normal has a mean of 100 and a standard deviation of 15. And the endpoint that we're looking for in this case is 115.54665. Another distribution that's useful is what is called the gamma probability distribution. So the normal and the uniform that we looked at, those are both symmetric distributions. We may be interested in what is called a right-skewed distribution. So remember, right-skewed looks something like this. Well, a gamma probability distribution is a set of distributions that are right-skewed. And so some examples that we might want to model using a gamma distribution are things like interval between telephone calls at a doctor's office or time before an earthquake strikes at a certain region. And so here we have pictures of different gamma distributions under different sets of parameters, very similar to what we saw with the normal earlier on. And similar to before, we're going to use R to help us calculate these probabilities just like we did with the normal. So here we do have the mean and the variance of the gamma distribution, as well as the necessary R code. Another one we may be interested in is the chi-squared probability distribution. You have probably heard about chi-squared test. So a chi-squared distribution is another continuous distribution, and it ends up that some statistics do follow the chi-square distribution, so that's why it's a useful distribution to know about. So I'm going to let you read about that one on your own, and you'll see that it is a special type of gamma. Another special type of gamma we might be interested in is the exponential probability distribution. And so here you can see a picture of some different exponential distributions. And we're going to talk about some of the properties of the exponential distribution and how that can help us. All right, so we're going to start out by considering any value a greater than 0 and b greater than 0. And what we're going to show is that if y has an exponential probability distribution function, then the probability that y is greater than a plus b, given that we already know that y surpassed a, is just equal to the probability of being greater than b. And this is what we call the Memoryless property. So it ends up that electrical components often have this property. So for example, we might suppose that A is equal to 5 minutes and B is equal to 10 minutes, then what we're asking in this case is the probability that it works at least 15 minutes, given we already know that the component worked for at least 5 minutes. And it ends up, this is just equal to the probability that it works at least 10 minutes. So it ends up that electrical components like fuses work this way, but a person's lifespan does not work this way. All right, so let's actually show why this is true. So if we consider the probability that y is greater than a plus b, given that y is greater than a, then we know by the definition of conditional probability that this is equal to the probability that y is greater than a plus b and y is greater than a divided by the probability that y is greater than a. Looking at the numerator, since b is strictly greater than 0, we know that that numerator just has to be equal to the probability that y is greater than a plus b, because if y is greater than a plus b, it's automatically greater than a. And again, this holds true since b is greater than 0. All right, so let's find these two different probabilities. We're going to start out with the probability that y is greater than a. Well, in order to find this, we are going to integrate from a to infinity, because we want y greater than a, 1 over beta e to the negative y over beta dy. And so you may ask, well, where is that coming from? Remember, we're working with our exponential distribution. So if we go back to the previous page, that is coming from right here. All right, so in order to do this, we're going to use du substitution. So we're going to let u be equal to negative y over beta, and du is equal to 1 over beta dy. So we have that the probability that y is greater than a is equal to negative a to infinity, negative 1 over beta e to the negative y over beta dy, making our substitutions is equal to negative e to the u du, which is equal to negative e to the u. Notice now, performing that integration, we have negative e to the negative y over beta, a to infinity, which is equal to negative e to the negative infinity over beta plus e to the a over beta, which is equal to e to the negative a over beta. And it ends up we could do something very similar with the probability that y is greater than a plus b. And it can be shown this is equal to e to the negative a plus b over beta. So now that we have found these two different probabilities, we can plug them into this piece right here. So we find that that conditional probability that we were interested in is equal to e to the negative a plus b divided by beta over e to the negative a divided by beta and that is going to simplify to e to the negative b over beta. And if we go back and we look at that exponential distribution, that is equal to the probability that y is greater than b. And it ends up that the geometric distribution also has this property. So why is this property useful? Well, the reason it is it relates to what we call the hazard rate function. So consider a positive continuous random variable x that we interpret as being the lifetime of some item. Let x have distribution function f and density lowercase f. The hazard rate, or sometimes called the failure rate, function lambda of t of f is defined as follows. Where here we have that f complement t is equal to 1 minus f of t, where that's the CDF. To interpret lambda t, suppose that an item has survived for time t, and we desire the probability that it will not survive for an additional time dt. That is, consider the probability that x is included in the interval t to t plus dt, given that x already survived t. So notice this is very similar to that memoryless property that we just looked at. And it ends up that we can show the following. Thus, lambda t represents the conditional probability intensity that a t-unit old item will fail. Suppose now that the lifetime distribution is exponential, then by the memoryless property that we just saw, it follows that the distribution of the remaining life for a t-year-old item is the same as that for a new item. Hence, lambda t should be constant. And in fact, you can show it and it checks out right here. Thus, the failure rate function for the exponential distribution is constant, and the parameter lambda is often referred to as the rate of the distribution. And it turns out that the failure rate function uniquely determines the distribution f. And so we could find that by using the following. So let's see this in action in an example. So one often hears that the death rate of a person who smokes is at each age twice that of a non-smoker. So what does this actually mean? Does it mean that a non-smoker has twice the probability of surviving a given number of years as a smoker of the same age? And so let's actually use what we just saw on the previous page to talk about what this means. So starting out, we're going to let we're going to say if lambda s of t, we're going to let it denote the hazard rate of a smoker at age t, and we're going to let lambda n be the hazard rate of a non-smoker at age t. So then, based on what we have up here, so we often hear the death rate of a person who smokes is at each age twice that of a non-smoker. So what we're saying here is that lambda s of t is equal to 2 times lambda n of t. So we're interested in the probability that an a-year-old non-smoker will survive until age b. And so here we're going to assume that a is less than b. So notice we could write this as the probability that the non-smokers lifetime is greater than b, given it's already greater than A. Right? Using what we have on the previous page, this is going to be equal to 1 minus F for the non-smoker at B, divided by 1 minus F of the non-smoker at A, which is equal to the following. I can show this simplifies to the following. And then we could do something very similar for our smokers. So we can show that the probability an A-year-old smoker reaches age B, and this is, considering that they've already made it to A because they're an A-year-old smoker. Well, it is equal to EXP negative A to B lambda n of t dt. And then all of this squared. And if you'd like to, you can show that on your own. One thing to notice, even though this is in terms of the smokers, we do have that relationship up above between lambda s and lambda n, so that's how we can make that conversion over. So what is this actually telling us? Notice here we have the same function, but the bottom one is squared. So what this tells us is that for two people of the same age, one of whom is a smoker and the other is not, the probability that the smoker survives to a given age is the square, not 1/2 of the non-smoker. So we do want to be careful when we hear about something as double, or what that actually means in terms of a death rate. All right, the last thing we have on this page, there is a relationship between the exponential and the gamma with the Poisson, and I'm going to let you read this last page on your own. And that's going to conclude this note set.